We're going to look at a few integrals that involve ln x, the natural logarithm. We'll start with this one, x times ln x. It's the product of two functions, which should make us think possibly integration by parts. The two functions don't appear to play nicely together. It's not like we've got two trig functions where there might be an identity that would be useful or a substitution that would come in handy. And it's not as if we have two functions that both involve powers of x that could be combined through multiplication. We have x and ln x, so integration by parts seems like a sensible choice. However, unlike x times sine x or x times e to the x, this one is going to benefit from a slight tweak to the method. We choose ln x to be the bit that gets differentiated, and we let x be the bit that gets integrated. It might seem a bit backwards. Usually we choose x to be u, the bit that gets differentiated, so that it gets simpler. X will go down to 1. This time x is going to get more complicated because we're going to have to integrate it. But the trade-off is that it's easier to differentiate ln x than it is to integrate it. So when we differentiate ln x, we get 1 over x. When we integrate x, we get x squared over 2. And if we apply the parts formula, uv minus the integral of v du by dx, we get this. Weirdly enough, even though ln x doesn't play nicely with powers of x, the derivative of ln x does. So when we multiply v by du by dx, those two terms multiply together to give something really nice. Some of the x bits cancel out with the 1 over x from the du by dx. And that means that we can actually integrate it. It comes out really nicely. Bit of a messy answer, but it works really well with parts, provided you remember to make u equal to ln x, so that this piece gets differentiated and not usually as what we normally do, where we differentiate the x part. Here's a couple of other integrals you can have a go at that use the same technique. It doesn't actually matter what the power of x is, unlike with things like x times sine x or x times e to the x, where perhaps increasing x to x squared or x cubed makes the process more complicated because you have to apply parts repeatedly. If you think about the way the terms cancelled out when we got to that final step, that technique is also going to work for pretty much any power of x. So have a go with x cubed or x to the half, that's the root x one, or x to the minus 2. See if you can make those work. And there is even a special case where we have x to the 0. If you think about it, the integral of ln x itself, I said it's not very easy to do. It's a bit of a messy result to remember, so most people don't bother memorizing it. But it's possible to calculate using parts. You just have to think of ln x as being the product of two functions, 1 times ln x. So if you make u equal to ln x again, and make dv by dx equal to x to the 0 or 1, however you want to think of it, then you can apply parts and get a result for this as well. This is what you get if you try the most general version, x to the n times ln x. If you've got dv by dx equals x to the n, you should be able to integrate it to get x to the n plus 1 over n plus 1. And as a result, when we put everything together, we get this general result. There is an edge case that I'm not going to mention at this stage, but you might discover it in a moment. Here are the specific cases for the questions you might have had a go at. If you basically replace n with 3 or a half or minus 2, this is what you end up with. And if you replace n with 0, you end up with the final result in purple. So they all look very similar. You can see the general pattern in there, and they can all be proved from one general case, which is what you've got over there on the left. What about 1 over x times ln x? This is a bit of an edge case from the previous one, because x to the minus 1 doesn't get integrated to give x to the 0 over 0. That would be undefined. It wouldn't make sense. But we've got a whole different technique we can use with this one. We can use substitution or inspection. We can think of ln x as being the thing we want to substitute for, and we know it's going to work nicely precisely because the derivative of ln x appears as a factor within the integral itself. So let's give it a try. If u is equal to ln x, the derivative du by dx is 1 over x, and that means dx could be replaced with x times du. The beauty of that is the x that we end up with will cancel out with the 1 over x that we've already got, and we end up with the integral of u du. which is really straightforward. The only thing we have to do at the very end is to go back and replace u with ln x. So the integral is ln x squared over 2. The reason I've said here that it's possibly also an inspection question is that if you notice this is the kind of result you might get when you differentiate ln x squared, then you could do that straight away. Here's a few similar questions that you can use to practice this technique. You'll notice that I've said we can try it with different powers of ln x. The beauty of this is that the 1 over x allows you to use a substitution, and so what you're left with at the end, if you try this with 1 over x times root ln x, the 1 over x cancels out and you're just left with root u, which you can integrate because you can integrate different powers of u. So you can give those ones a try. You'll notice the last one looks a little different because it's got x cubed, but it's still possible. Things will sort themselves out fairly nicely with that one, as long as you apply the same substitution. You might be thinking, why can't we use integration by parts for this one? We did for x ln x and x cubed ln x and so on. Well, you could, but if you try it, this is what happens. You end up getting back to where you started. The integral of 1 over x is ln x, and the derivative of ln x is 1 over x. So all you end up doing is proving that your integral is equal to ln of x all squared minus your integral, which might sound like you're going in circles, but in fact this particular equation is not impossible to solve. It's actually really quite straightforward. We're not saying that x add 2 is equal to x add 2. It's more like we're saying x add 2 is equal to 5 minus x. That's an equation that can be solved to get a sensible answer. You just have to move the I onto the other side. You get 2i equals ln of x all squared. Divide by 2, we get I. This next one doesn't appear to involve logs at all, but I'm showing it because it illustrates a really, really important logs result. If we can write the integral as a fraction where the numerator is the derivative of the denominator, then we know from chain rule that it's going to integrate to ln of the denominator. Think about what happens when you differentiate ln of a function. You get 1 over the function multiplied by the derivative of that function. So with tan x, I've just got to do a slight rewrite. Tan is sine over cos, and because the derivative of cos is minus sine, I'm going to pull out a minus sign, so I'm thinking of sine x as minus sine x. One of those minus signs gets taken outside the integral altogether, so I don't have to worry about it. And now my integral is perfectly in the appropriate form. The numerator is the derivative of the denominator, so the integral is just going to come out as ln of the denominator. The minus sign is still in front, so minus ln of cos x. And at the very end, if you like, you can even bring that minus back in using the log rule that says a number outside the log can be treated as a power of the contents of the log. And I've done one last thing. If you have cos of x raised to the power of minus 1, that means the reciprocal of cos of x, which is sec x. And this is a result which is in the formula book, but now you've got a proof for it that uses the log trick. A log trick, incidentally, which you'll find helpful in all sorts of different situations. Have a look at the denominator, see what the derivative would be, and see if it's possible to scale things so that the numerator matches the derivative of the denominator. If you can do that, you'll be done. Here's a bit of a sneaky one. It'll take a bit of rearranging, but it's a similar trick. So if you can find a way of writing it so that the numerator is the derivative of the denominator, then the integral is just ln of the denominator. This final section is a couple of trickier integrals involving logs. This one has come up on a past paper at some point, the integral of ln of x all squared. Now, it's not particularly obvious what the best technique would be here, but the fact that we've got a function multiplied by another function suggests that maybe something involving integration by parts would be useful. You can play around with some different methods here, but the method that seemed to make the most sense to me was the same one that we would use for the integral of ln x. It just takes a little bit longer. So I'm going to use parts, but again, I'm going to insist on making u equal to the square of ln x. Just like when it was the integral of ln x, I made u equal to ln x because it's easier to differentiate it than it is to integrate it. If we do that, we have to treat the other term in the product as just the number 1. So we're thinking of it as ln x squared multiplied by 1. And the 1 is the other function that goes into the parts formula. That's the one that's going to be integrated. So 1 becomes x. Ln of x all squared with a bit of chain rule becomes 2 lots of ln x multiplied by the derivative of ln x. When we throw all that in, we get this. We're not quite there yet, but we're closer, because all we'd need to do to complete this is find the integral of ln x, which is still something that requires integration by parts, but at least once we've done this piece, we'll be there. So I would make a new letter. I normally use capital I to represent the integral I'm trying to find. I'm going to use capital J as the next letter along to represent this integral, which is going to be important integral, if you like, in producing the answer to the original problem. So we deal with this using parts. U equals ln x, dv by dx equals 1. Integrate one, differentiate the other one, put it all together, and we can find the result for the integral of ln x. And then I'm going to throw that into the original expression for I, x times the square of ln x, take away 2x times ln x plus 2x plus c. You might notice I've used c1 here and then c here. What basically happens is when I compute an integral, I have to remember to include a plus c. If I find later that the constant has changed, this is a lazy way of going back in hindsight and changing so that I'm not pretending that the c is the same c as it was before. They're both arbitrary constants of integration, but maybe the second one is the negative of the first, or maybe it's minus 2 times whatever the first one was. And in order to not confuse things, I just give the first one a different name. Call it k, call it c dash, call it c1, something like that. If you want to try this kind of technique for yourself, you could have a go at the integral of ln of x all cubed and see if you get the same answer that I've got up on the screen. It will require you to do parts even more times, but if you've already got this result from the integral of ln of x all squared, you can make use of it as part of your process. And then if you want to have a go at a slightly different one, try the integral of 1 over ln of x, which I think can be dealt with in a similar way. Think of it as ln of x raised to the power of minus 1 and see if there's a way to break that apart using integration by parts. Good luck.